about everything in the society. I'm currently Vice President, and probably the most qualified, or one of the most qualified, given you joined, was it 1966, to
66,
yeah, talk about this, the history, basically the history of the society.
Not quite. I'm talking about the history of astronomy over the period there.
Oh, okay, so, right.
I'm talking about the society.
There'll be some connection to the society,
will,
I'm sure. So, okay, thanks very much for coming along, Grant.
It's a great pleasure, Bill. So, thank you very much. Do I have something to add?
Oh, hit the space bar.
Okay, so well, thank you for coming along. It's nice to see people in person. So what I want to do is just sort of talk through the what happened in astronomy over the time the society existed. It was formed in 1923 on the 23rd of March by Professor Percy Burbage. He was Professor of Physics at the University of Auckland. He got interested in he was interested in astronomy for a long time, but he was away at Cambridge and he did a Master MA at Cambridge, a very good one apparently, and was given the offer of a professorship at Auckland for physics. So he was coming back to be head of department. He was on a ship coming back to Auckland, and he got talking to another academic who was on the ship, and informed that Yale University in the United States was looking for a place to put in a big 26-inch refractor somewhere in the southern hemisphere to supplement their work in North America and the northern hemisphere. So Burbage was really, really keen to get that 26-inch telescope in New Zealand, preferably in Auckland. And looking back now, it was a bit of a stretch, but nevertheless, they put a lot of energy into it, about a year testing the skies around. Yale provided them with testing telescopes, and they had to check the seeing and all that. But just cut a long story short, eventually they pulled the plug after a year or so. They could see that Auckland skies were rubbish compared with other places like South Africa, so the telescope ended up going to South Africa. But anyway, sort of in parallel with this, Burbage also decided to convene a meeting of people interested, and they called it the Auckland University College because that was what University of Auckland was called then, interested in forming an astronomical society. And so that was on the 23rd of March, so nearly 100 years ago. That's when the society was founded. And I think they started off with, I'll just push this. So they started off with a very small number, and it never got very big. So the society never got much momentum through until the 1950s. So I'm not talking about the society's history. It's interwoven with the talk, I guess, but I'm mainly talking about how did astronomy change over the century that we've existed? And I think it's quite remarkable when you think about it. So, and I've only picked out things that I thought were important. There were lots of things happening every year, but these I think were the ones that were notable. So in 1929, Edwin Hubble famously discovered that the universe was expanding. This was a complete out of left field discovery. Nobody even suspected it. He did it by looking at for pulsating stars called Cepheids in neighbouring galaxies, and was able to use them because you could actually work out the true brightness of those objects. It's called the period luminosity relationship of Cepheid variables, and they were able to, once he found those in nearby galaxies, which was a real stretch with the 100-inch telescope, it could only just do it. It was right at the limit of what it could be done. And he actually found enough of these Cepheids and worked out the distance of these galaxies, and when he did that, he found that the further away the galaxy was, the faster it was receding. And he hypothesized that the universe was expanding on the basis of that. It was a pretty big call to make at that time, but it proved to be correct. And so in 1930, this guy here, Chandra Seeker, who was just 20, he figured out what a type 1a supernova was. These are stars that explode. He figured out, he was looking at the mathematics. He was a theorist of white dwarf stars, which are very dense sort of remnants of main sequence stars that they eventually evolve into. We knew a number of those. Sirius B, for example, a star going around Sirius as a companion, is a white dwarf. And one day Sirius will end up as a white dwarf as well. But that's a natural evolution of stars in that sort of mass range. And if the white dwarf is in orbit around another star where it's sucking material off it, then it gradually gets too much mass accumulated on it as it sucks off its companion, and then it detonates in a supernova explosion. So that's called a type 1a supernova. And so Chandra Seeker was looking at the properties of these, and he proved that, in fact, if you have, once a white dwarf gets to 1.44 times the mass of the Sun, 44% more than the mass of the Sun, it will detonate. And absolutely inevitable, it will produce a type 1a supernova. So they've been extremely useful explosions because they all have the same brightness. So today we see type 1a supernovae in thousands and thousands of galaxies. They're mapped all the time, and they give you a really good indicator over cosmological distances. So this was the first stuff. But Chandra Seeker did all sorts of fantastic stuff. He ended up as a professor at Chicago University, and he was a very distinguished career in astronomy and astrophysics. And he was editor of the Astrophysical Journal, which is the most important publication in astrophysics and astronomy. So he was that for many years. So he was quite an interesting character. Can I go forward too many? Probably, yeah, just, there we go. So the other thing that's I thought definitely deserved to be here is the discovery of Pluto. Although we know Pluto is really it's not a planet, but that's not what was known at the time. It was discovered in 1930 by this guy, Claude Tombaugh. He was working for Lowell Observatory, and his job was looking at photographic plates. They were taking photographs of the night sky, looking for asteroids. So he'd be getting these big glass plates about this size, peering over them and blinking them with another one that was taken at a previous time, and that would show up anything that moved. So you'd get these things lined up with binoculars vision, you look in there, you flick them backwards and forwards, and anything that's moved in the meantime jumps back and forwards in front of your eye. So Clyde Tombaugh, that was his job. And in the course of doing that work, which must have been unbelievably, well, I guess he liked doing it, but he actually found this object that moved, and went and looked at other plates, and it turned out to be Pluto. And the more they followed it, they eventually worked out its orbital period, a couple of hundred years, and it was actually relatively bright. So they thought it was big, and it was clearly in a long period orbit out beyond Neptune, but they assumed it was quite a big object, and it became basically the 10th planet of the solar system. Ninth planet of the solar system. So but we know now that it isn't. It's actually a small body, and I'll talk about that a little later. But that was a biggie at the time of 1930, and that's not the telescope he used, by the way. That's just he was a very keen amateur astronomer, and but incredibly dedicated and proficient. 1938 was when Hans Bethe explained how stars produce their energy. So that was not known. Nuclear physics was in the infancy at that stage. So how did stars produce all this energy and keep burning for such a long period of time? And this was the conversion of hydrogen into helium, and Bethe was one of the people that worked out the nuclear reactions that must be going on inside these stars in order to produce that amount of energy. And of course, when you've got a big star, that means you've got a lot of fuel, so stars last a long time. And it's sort of like a regulated thermonuclear furnace inside the core of the star, and it's the heat going out that stops the star, just holds it up against gravity, stops it collapsing over a long period of time. But he also was a theorist that contributed in many, many different parts of astronomy and astrophysics. Jumped over a few years, but 1944, at the end of the Second World War, the Germans had built the V1 and V2 rockets, which were sort of way ahead of what was available on the British and the Allied side. But at the end of the war, the Allies then got hold of him and his rocket design ideas and gave him a new job. And that was developing spacecraft that could be capable of getting off the planet and actually doing stuff in space. You could actually launch satellites with rockets of this general idea. For example, the sort of things they didn't know was, would a rocket, would they work in a vacuum, for example? So some of these things, the technologies of those had to be sort of worked through. But Vern Von Braun ended up doing a lot of stuff with NASA for the rest of his life. He joined the A team, I guess. And then 1948, bit of a jump again, but the Second World War, nothing much happened in astronomy and astrophysics. People had other things to do with their time, but like building atomic bombs, which was still good science in its own way. But in 1948, they completed building, it took 10 years, over 10 years, to build the 200-inch telescope at Mount Palomar. So that was a big step up from the 100-inch telescope at Mount Wilson, run by the same observatory network. And it cost an enormous sum of money. But it's still a potent telescope today. It's what we call a 5-metre telescope. Today we have telescopes that are 10 metres, and some even bigger ones are being planned, like 26-metre telescopes with segmented mirrors. But this one here, the mirror is all just one single slab of glass, and technically actually pouring a piece of glass that's 5 metres across and about that thick, and not ending up with, well, you don't want bubbles in the glass when you start to sort of polish it and do all that sort of stuff. You don't want any of that sort of problem. So it was technically quite an achievement just to make the primary mirror. But so that telescope still functions at Mount Palomar. It's not in the A team anymore because it's a bit too small, but it's still got fantastic tools and equipment with it. So 1956, we get up to the time of the Auckland Observatory. What sort of started off the observatory, which was important to us here locally, was that Edith Winstone Blackwell, the lady in the photo, she had had a lifelong interest in astronomy from the time she was a little girl. So, and she had, in fact, we've actually got her little book of constellations and things, which is, the family gave us. But so all through her life, she was dead interested in astronomy. She was part of the Winstone family, so they were well off financially. So she was able to do a lot of stuff. She did a lot of social stuff. For example, funding from her and her bequests later in life funded a lot of the marine lab up at Lee for the University of Auckland. I think at least $1 million. And she also provided, she was interested in astronomy, of course, so what she wanted in the 1950s, they were talking about building an observatory in Auckland, and there was a lot of stuff in the press about it. People wanted to do this. The society was fairly disorganised. But Edith Blackwell, nothing new, you reckon? I don't. Anyway, so she wanted to donate a telescope for the citizens of Auckland, and so I remember Arthur Partridge, who was our president at that time when I joined in I joined in 1966, but about 1960. Well, by the time I got in there, I'd heard the story so many times. But Arthur Partridge had her coming round to say, I want to come round, or her husband said, I'll bring Edith round and we want to make a donation to your fund to raise a telescope. So, he'd been thinking, oh, well, that's great. We'll get a fiver out of this, £5, £10. It was a lot of money then. So she came around and donated, I think it was £7,000 or £8,000 for a telescope. So all of a sudden they had said, you find the telescope and that's what we can pay for it. In the end, over the years, it actually ended up a lot more than that, and they sort of forked out more for it again. That's why it's called the Edith Winstone Blackwell Telescope. But So anyway, they did get a contract with Zeiss to supply the telescope. They got the prices from lots of different people, and Zeiss's was probably the best offer. And then they had to find a place to put the telescope, and that became a story in its own right. And we ended up being very lucky to get it where it is now in One Tree Hill. 1957. So this is into my era now, because I was 5 years old then. So I remember this, surprisingly. It stuck in my mind because I was 5 and staying with my grandmother in Balmoral as a special treat. It was, you always sport your rotten. And she had heard about this satellite that might be going overhead, and people like Ron McIntosh in Auckland would have been talking to the press saying, you know, you probably could see it if it went over. So, but they didn't have times or anything. The Soviets weren't giving away all their orbital information. It's not like today when they still don't. So I remember being carried outside with her to look up in the sky to try to see this satellite, which we didn't see, but nevertheless it was something that stuck in my mind. So that was Sputnik 1, and there were other Sputniks as well, but that was the first Earth-orbiting satellite, 1957. 1958 was the founding of NASA. So this was it was an agency. It was created by the USA, basically to coordinate all their research in astronomy, astrophysics in particular, and observational stuff with telescopes. They were very competitive with the Soviet Union, still are, of course, so they didn't want the Russians to get dominate space, basically. So the NASA and the government in America, or the government put a lot of money into NASA to say, lift your game, people. So NASA was founded in 1958. 1961, Yuri Gagarin became the first, a Russian, became the first person to orbit the Earth in a very simple rocket by our standards. The fact that he actually, as he was coming back down to Earth, he then bailed out and came down on a parachute, gave the Americans the chance to say, well, he didn't really bring his rocket down. So, Alan Shepard, thank you, did in fact come right down in his tin can. But anyway, that was that was what things were like in the 50s and 60s. So that became quite important because it actually was the start of the space age. And then 1962 was the Mariner spacecraft. So this was the first spacecraft to visit another planet. And it flew past Venus. Venus was not well known. It was known that it was covered with clouds, but nothing much else was known about it. It was thought that underneath the clouds there was sort of this very humid, temperate, because it's closer to the sun, and they imagined a huge, sort of a place that like a tropical rainforest kind of scenario. If you look at the books written in the 1950s and 60s, that's the sort of story that they had. So they sent, this was the first probe that actually reached another planet. That was what's notable about it. It just flew past and took pictures and said, it's cloudy, we can't see anything. I probably found other things as well, but 1963 was the discovery of quasars. So Martin Schmidt, a Dutch-American astronomer, these objects were, they looked like stars, but they had the wrong spectrum, and they were also, from the shift of the spectral lines, the Doppler shift, they knew that these things were a hell of a long way away. So why did they look like stars, and how could they be so bright? How could something several billion light years away be so bright that it just looks like a 12th magnitude star, which you could see with an amateur telescope in your backyard? So that was the puzzle, and it wasn't until Schmidt and others took spectra of these things. That's an artist's impression, not a photo, but so they were just seeing a single star sitting there, And when they worked out the distance, they realised that these things were cosmological. And it was then that they proposed that in fact the only thing that could produce that, as far as they knew, was a black hole, a massive black hole, sucking stuff in, and as the stuff fell into the black hole, huge amounts of energy were radiated away into space. And so they realised fairly early that black holes were the only reasonable explanation. But if you look at Scientific American articles in this period, you'll find sort of other ideas were suggested, but they never flew very far. 1965, and this was a really important discovery. Penzias and Wilson were interested in just exploring the universe, and they built a horn, which was basically just to detect very low frequency waves. And it turns out that they did find a signal coming from basically no matter where they pointed it, it was always the same. So this whole sky was just sending them a signal that had a temperature of 3 Kelvin, 3 degrees above absolute zero. So it was a very weak signal that was constantly arriving at the Earth. And the explanation, as it turned out, which they proposed, was that it was the remnant of the Big Bang. And so basically the whole universe was, although it was expanding, there was this radiation, very weak radiation coming back from that was the remnant of the Big Bang explosion. So the Big Bang was hot to start with, but as the universe expanded and cooled, the temperature of that radiation filling space got down to 3 degrees Kelvin. So that was a very important discovery. They got the Nobel Prize. Not bad. So then about 1965, we had the first ideas. Well, the observatory in Auckland here had been being kicked around for quite a long time. And there was stuff in the press about it. Edith Winstone Blackwell had agreed to donate this telescope, and she had died already by this time. And so she had left this legacy. And so there's a lot of stuff in the press. People like Ron McIntosh, who used to run the planetarium at the museum. I don't know if any of you ever went to the museum, and a few of you, yeah. So McIntosh was one of the sort of key people in the Astronomical Society. And in his older age, he was running the planetarium at the Auckland Museum. So if you went to any of those shows back in the sort of 60s and 70s, then there would be this old guy in the corner sort of talking softly while he was pointing his pointer around. That was around Macintosh mostly. So he was always sort of talking to the press about getting money for this observatory project. Finally, the trustees, the members of the trust board, had got together an architectural firm to come up with a conceptual diagram. It doesn't look too different to what we actually got, except that what you see today, it's 4 times the size. This is all the front. That's not the front door anymore, the front door's kind of a new bit of around the corner. But you can still go in and out of that door, which you probably found on Society Nights. But it's but essentially that was the proposal, and that was in 1965. 1966, the biggie here was the landing on the moon by the Russians of Luna 9, and so followed shortly after by the Americans landing their Surveyor 1 on the moon. So these were both soft landed on the moon, technically quite a technical challenge at that time, considering, you can just think what the technology we had in 1966 was like. You sort of sending something off to another, like to the moon, and you wanted to land on the moon without crashing. It was really quite an achievement. So both of these, the Russians did it first, but the Americans came in a bit later with a more sophisticated lander that worked for quite a long time. Thank you. 1967, that was the discovery of the first pulsar. This lady here is Jocelyn Bell Burnell. Jocelyn Bell, she's was a student at Cambridge University when she was young and was working on radio astronomy with her supervisor on the right-hand side here. Hewish, and so they had at Cambridge this big sort of layout of wire mesh. Tim would know a lot more about this than I do, but anyway, it was a very crude sort of detector trying to detect radio waves from the universe, and Hewish had started that off, but Burnell, Jocelyn Bell, sort of was making it work, and she kept. Eventually, she found that there was a signal produced on this radio. So you imagine this big, huge field with all this wire mesh everywhere, and that's picking up signals from space. I'm not a radio astronomer, but anyway, it ends up. She was getting this blip on the traces of the detector of about a 2-second blip every 2 seconds. It goes blip, blip, blip when a certain part of the sky was going over. So she had gone through, and there must be something wrong, and sort of worked on a scare trying to trace any way that the mesh could, or the thing could be a fault in their system somewhere. But she failed to convince her supervisor, who still reckoned it was just noise from some factory or something in the vicinity of the stuff around Cambridge that was producing this anomaly. But anyway, so Bell didn't sort of agree with that, but anyway, it turned out that, and she persisted and was able to sort of basically prove that there was something astronomical or astrophysical going over, and it was producing that, and it turned out to be a pulsar, the first detection of a pulsar. And a pulsar is just a rapidly spinning neutron star. So what happens after a supernova, the core gets crushed down, so you've got this massive star sort of turning around on its axis. When it runs out of fuel in the metal collapses and it explodes in a supernova, and the core gets crushed down into a really, really tight thing called a neutron star, which is only a few kilometres across, but it's incredibly massive. So it's got a huge amount of mass crushed into a little space. And as it spins, it radiates radiation out through its axis, and as it sweeps across you, you get this blip, blip, blip if it happens to be facing the right way. And that's really what they were seeing. And so it was indeed a neutron star, and nothing to do with noise. But Hewish still received the Nobel Prize for it. You should hear her talking about it today. But that's why it was a bit suspect. But so Hoyle and Gold also got shared that Nobel Prize as well. But so I mean Hewish and Ryle, sorry, were. Yeah, I don't know where Ryles was involved in it, but Hewish certainly was not supposed to. I mean, I know that Hewish was her supervisor, and that was a sort of big issue. So, I mean, she's visited here a few times, and obviously this is a subject she talked about when she comes here. So, do you remember, Bill?
Yeah.
Yeah. So anyway, so. Unfortunately, she didn't get the Nobel Prize, but she got many other distinguished prizes as well instead. And then in 1967 was the opening of the observatory. That's what it was. That was the courtyard, which is built over now. So that's all built over, and this is beyond that is where the planetarium roof is. That's not there in this. it was always planned that there be a planetarium of some sort there, but it was not possible to fund it right at the beginning. So that was the observatory, as I remember it. I remember it had only just opened, I'd only just joined. In fact, I remember when I wrote this formal letter of application to join this august body called the Astronomical Society. I'm probably the only person who ever did that. In my fourth form neat handwriting, I was at great pains not to mention anything about the observatory because they thought, well, we don't want him because he's only interested because we've got an observatory. So that was the way my mind worked at that time. Anyway, I didn't realise they just took anybody. So welcome. Anyway, so the meeting I attended in about March of 1967 was the first time the society met in there, and it was all shiny new and smelt new, and it was really pretty amazing. And the Zeiss telescope was brand new, which was was fantastic as well. Biggest telescope in New Zealand at that time. And I might say that although Winston Blackwell donated the money for it, the Winstone company, which is in the building industry, did a huge amount, provided a lot of stuff for at cost or nothing, provided a lot of technical expertise to get the building done at an affordable rate for us. So that was fantastic. So 1968. The Apollo 8 mission to the moon. That was, it was the first time that humans had gone outside the Earth's gravitational field to another body, so that was notable in that respect. I remember it extremely well. But during the Apollo missions, there was a group in the United States tied up with the Smithsonian Institute that was trying to organise people to keep a close watch on the moon with your telescope all the time that the astronauts were in the vicinity of the moon. Because for the first time, because there have been reports for decades about things that were generally called transient lunar phenomena, little flashes that they'd see. Well, you'd imagine if a rock hit the chunk of the moon, it could easily create a little bang, and there's no atmosphere to stop rocks hitting the moon, and it's covered with craters after all, so yes, you'd expect to see that. That would be interesting. It would be interesting, of course, if there were volcanic activity and there were outbursts of gas or any sort of show of eruption. We know that there's volcanic activity on the past on the moon. And there's this other things that people had been reporting for years where they'd see a flash for no particular reason. The crater Aristarchus, for example, was a prime example of a source of those sort of things. And it could be that it was ice sort of on the bottoms of craters or something about the sort of the surface there that just reflected light in a particular way. But anyway, they were generally called transient lunar phenomena. They were sort of it was a bit like, I don't know, it was a little bit fringe in astronomy. But we were asked there was a worldwide call out for telescopes to look at the moon while astronauts were in the vicinity of the moon. So we put our hand up and we did that using the Zeiss telescope. Initially it was just looking through the Zeiss telescope to see whether we'd just pick an area of the moon. In fact, Harry Williams, who so many of you all know, late Harry Williams, he was a great telescope maker and stuff here in Auckland, very long-term member of the society. He was an old man when I was joined, or getting old. Anyway, so he and I sort of started a project during the Apollo landings when there were astronauts there to look at the moon through the Zeiss and just watch some of these areas and see whether we ever saw a flash. We didn't, but anyway, you never know, you've got to give it a go. So we got involved with the Apollo missions because of that. And so in '69 we had the Apollo 11, which was, of course, hugely important, the actual landing on the moon. Again, the same applied because Collins was still orbiting the moon, so he was keeping the moon under watch and going around and round and round while his two companions were down on the ground. And so on clear nights we were using the Zeiss telescope to watch the moon. But by 1969 observatory had just managed to build a photoelectric photometer, which is a very sensitive light detector. And you don't point it at bright things, so sort of pointing at the moon, it's normally just intended for relatively faint stars. But Harry Williams and I decided just to point it at the crater Aristarchus because that was something that he had studied, and also there was a crater that had this sort of history of little flashes and things. So we thought, oh, what the hell? Well, our detector was very sensitive, so we just pointed it at this crater of Aristarchus while it was in the shadow. It wasn't illuminated by the sun, so it wasn't too overwhelming. We did that through all the Apollo missions while there were people there. Up on the moon, but we never saw any flashes. You got to try. But anyway, they got a lot of press because the observatory could say, oh yes, we're part of this NASA, worldwide NASA campaign, blah, blah, blah. I mean, that sort of meant people came along to the observatory and wanted to see what was going on. And so this is what the telescope looked like in 1969. So, in this instrument here that Roger Feasey is using is the photoelectric photometer, which is a very sensitive photomultiplier cell in here, a wide field eyepiece, just like you'd have on your own telescope. Flip a mirror up and then you look through this microscope eyepiece because the field of view of the photometer is only sort of like 10 arc seconds or 15 arc seconds across, so it's you just put one star in it, that's the idea. And so that's what's doing there. And in here there's a very sensitive electronic cell that responds to extremely low light, and that for many, many years was our primary instrument. Mainly, the moon was extremely unusual to use it on the moon. It was mainly used for the study of variable stars. And
I was just going to say, I think when I joined, Roger was president of the society.
That's right. Oh no, well, Roger and I met at Mount Abbott Grammar School. So I joined in '66. Roger joined in '68 because I started an astronomy club at Mount Abbott Grammar School and we got friendly. So then there was, so Roger and I were members of the society. Roger Freeth, who some of you might know the name Roger Freeth, he was a motorcycle racer and rally driver. He was killed in a rally crash in Australia, unfortunately. And Ian Thompson, who you won't know, but he was a member of the society when I joined, same age as me, and a really top scholar. He ended up doing extremely well academically, and he now lives in Britain. But so there were four of us, four junior members of the society. That's pretty much all there was, and we all ended up doing PhDs. So I don't know what the chance of that would be statistically, but it was a sort of a very exciting, interesting environment for young minds, let's say. So, sort of, it's good for people to do this. So anyway, so the photometer was built. Harry Williams did all the structure. Clive Rowe in Canterbury University did the electronics, which he invented, and the physics department chipped in with instrument things for things like this thing here. That was our clock. You probably recognise Kirsten clock, circa 1965. That was our time source. The number of counts, the number of photons was coming up on that thing there, and you'd just write them down by hand. And seeing that picture, I hadn't looked at it for a while, but that is the exact pullover. And not only that, it still fits. My dear grandmother knitted that for me. Oh yes. Anyway, so. Oh really? Yeah. So anyway, so basically that's what we were doing with during the Apollo mission at the observatory. But so just as the science was going on, so 1970, that was just around about the time of the missions. So NASA had built the Uhuru satellite to look at the X-ray sky of the universe, which nothing had ever been done like that before. You can't do that from the Earth. And the satellite ended up charting and identifying 300 X-ray sources, and several which were possible black holes. So this was all completely new science. Black holes had been hypothesized. Nobody had ever actually really proved that they existed. So that was important. And they also, this mission also proved that neutron stars were indeed created by supernova. So that was the Yuri satellite, and the Vela pulsar is buried in there somewhere. Tim would know more about that than I would. You probably looked at the radio tower there, didn't you? Or looked, in inverted commas. Pretend you could see it. 1971, so both the Russia, or the Soviets, and the USA were very competitive in space because there was a strategic advantage, and they were talking about ballistic missiles and total destruction and all that sort of stuff was the sort of jargon of the day. So they didn't want the Russians to get too far ahead, but anyway, the Russian launched its first space station, which went into orbit and stayed there for a period of time. So they were able to send astronauts up there just like today with the space station, but this was the forerunner of the space station, basically a simple one. But it meant you could stay up there for a long time. You could have astronauts up there cycling around, and you just send up another spaceship and bring them back. 1972, this was the first evidence, absolutely irrefutable evidence of a black hole. It's a massive, it was once a binary star. This one here is now a pulsar, so it was actually the more massive of the two, so it actually chewed through all its material and blew up and became a supernova. That left that there, and its companion was still there and became a donor star, so material was being pulled off the star into this. So this was all completely new stuff. If you look up the stuff in the 1960s and 70s, this was sort of frontier of astronomy. We now know lots and lots of these and understand the physics, or not we, but them, the people who study these things in detail. But it was, and it was called Cygnus X1, but so basically there's a black hole in the middle of that, and that was once the more massive of the two, of that massive binary star system. So we now know there's lots of these things around, which get studied by big observatories. 1975, we had the Soviets managed to land a probe on the surface of Venus, soft landed, and it actually sent back pictures. So we'd seen the outside before, but hadn't really had a good look underneath, and so Venera 9 actually got down to the surface. Didn't last very long because it turns out 400 Celsius on the surface. It sent back that little picture. This is an artist's impression, I hope, otherwise it'd be very hot. But this was the first probe to land on another planet and the first to orbit Venus. So that was the first soft landing of anything on a world other than the Earth. But I remember that picture when it was in the newspaper. It's curved because of the optics of the lens, not because that's the shape of Venus. So then the next big thing, which were really important, was the Viking spacecraft. They were NASA's project, and they sent these two spacecraft to Mars. Each one was so that each Viking craft was an orbiter, and it also had another part that could drop off and go down to the surface. And there were two land in different interesting parts of Mars that NASA was interested in. But the primary thing at that time was there was still considerable discussion about whether Mars could harbour life. So that's what the missions were there. They were there to look at the chemistry, to see in the atmosphere, and to try to see whether there was any evidence at all of life. So I don't think it's been ruled out yet. Then this was one of the most amazing projects that NASA came up with, which was the Voyager 1 and 2. These were craft that they launched because there was, for a time in the late 1970s when all the planets, except Pluto, were all the outer planets, which from Earth you'd have Mars, Jupiter, Neptune, and Uranus, all lined up. So you could actually send a spacecraft out that could just go one dong, 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 dong and hit them all. Normally they'd be any which way and you'd only hit one planet. So this was a rare, never to be, well, could be hundreds of years away from ever happening again. So NASA put all their effort into getting the Voyager spacecraft to take advantage of this unique alignment of the planets. So Voyager 2, it went to, as you can see here, it went to Jupiter, Saturn, Uranus and Neptune, and then out onto the Kuiper Belt, which was sort of a debris belt out beyond Pluto, and finally into the, it left the heliosphere and finally into the interstellar medium. So it stopped working in about 2018. Voyager 1, however, is still going. I was surprised when I checked up on that. Did you know that, Tim? Do you ever talk to it?
Tried to listen for it, but failed.
Yeah. Anyway, so Voyager 1 is amazingly still alive, launched in 1977. And, but I don't know if it's got much to say. It's probably in the middle of no place and looking around. So the Voyagers were a phenomenal success and sent back amazing images of all those outer planets. 1981, the Space Shuttle Columbia. That was the first reusable space shuttle. America put a huge amount of effort into this. The cost of sending up a bunch of hardware and then trashing it and having to do it all over again. They decided they had to build a space shuttle. The other thing is when they came to build the space station, this was critical in being able to take bits up with lots of people to assemble a space station. If you were doing that on throwaway rockets every time, it would have been enormously more expensive. So they ended up with a shuttle fleet of a number of these shuttles, and they were, on the whole, extremely successful. And the IRS Satellite, it got launched in 1983. So this satellite, I mean, some of the data from these we just use routinely today. So the IRS Satellite was infrared, and it surveyed the entire sky, 98% of the sky. The camera had to be cooled right down to close to absolute zero to get rid of the noise, but it surveyed the entire sky and produced this vast catalogue of infrared sources in the sky. So it's still, you know, still a fantastic achievement, particularly for that time period. And it's one that you go online, you'll still look up stuff in the IRS catalogue. Oops. Thank you. So, in 1986, Halley's Comet came back in its 76-year period or something like that. But anyway, it was the... 76, yeah. So 76 years it comes round. So that was again a time-critical thing to launch to intercept Halley's Comet, to get a really good look at quite a big comet. So ESA produced Giotto, and it ended up flying through the Halley's Comet's coma and imaged the nucleus from a distance of only 600 kilometres. So it was pretty amazing. That was by far the closest look I think we've had on a comet even today. And sort of that year too, the Challenger exploded just after launch. That was lost a shuttle. 1989, we had the Magellan probe from NASA went to Venus, and unlike previous times at Venus where they just saw cloud, this one was working using basically infrared and radio is it? Yeah, radar mapping of the surface of the planet. So they could look through the atmosphere and see what the surface and terrain was. This is just an example picture. So it spent 3 years mapping it. So we got detailed map of the geography of Venus. You wouldn't want to go there, but it's and has no practical purpose. But the main thing, I guess, from the point of view of Venus, is that it's very similar mass to Earth, so it tells people interested in the formation of planets and stuff like that, and the formation of atmospheres. You know, Earth and Venus side by side provide quite a good contrast for that sort of work. The Hubble Space Telescope was launched in 1990, and we were all tremendously excited because this telescope was going to be the bee's knees until it found that it had an error in its optics, which was an unmitigated disaster. The mirror had been perfectly made to the wrong shape, which is the way to describe it, and you can only feel for the people who did that. It was just a little tiny accident in the setup, which was never noticed until the telescope was in orbit. So you can't bring it back down and you can't get the mirror out. So NASA had to come up with basically an optical correction for that. Once they worked out what the problem was, they were able to design a set of optics which, when fitted in front of the mirror, were able to correct that completely. So we had to wait another 3 years before that actually ended up happening, and then from then on we've had sort of absolutely fantastic images from that telescope. And it's still, although the James Webb is much bigger and has other stuff, the Hubble's still strongly competitive in its own way. It works more in the optical wavelengths and the infrared. 1995 was the first discovery of an exoplanet. That's a planet orbiting another star. So you'd think that's actually not that long ago. So that was the first time we have them. We now know lots and lots of exoplanets. It's basically, you know, it's what we've been doing at the observatory for quite a long time, is through microlensing, is detecting them. So this was the first one. This was actually able to be detected because this planet here, which was sort of Jupiter-class planet, as it orbited that one, it pulled the star backwards and forwards, and so as it did that, the spectral lines in the spectrum moved backwards and forwards because of the Doppler effect, and they were able to work out that that star there was being orbited by that planet. They didn't pick the star at random. I mean, well, they did. They just picked a whole lot of stars. They knew that sooner or later they'd get a Jupiter that was close enough to its planet, to its star, that it was giving the star a little bit of a tug that would be detectable, and sure enough they found it, and they found thousands more in that, using that technique, the radial velocity method. And that's only 1995, it was discovered that the universe is now expanding at an ever-increasing speed, and it's driven by dark energy. So that was completely out of left field, basically. It came that once they were able to sort of map the universe on large scales, they were able to work out that from the Big Bang, things expanded, but now we're at a time, this is the time we're at now, the universe is expanding at a faster and faster rate. And so that was unexpected. But in fact, you have to know there's no speed limit on the expansion of space. So the universe can expand faster than the speed of light. It's not limited by that. The speed of light is only a limit within a reference frame, but if your reference frame can expand as fast as you like. So that's the paradox there. So this was a big discovery. So they found that dark energy was a large fraction of the energy content of the universe, which was completely unknown until this era came along and the theorists worked this out, confirmed by observations. Well, 2003 was the Shuttle Columbia disintegrated, coming into the atmosphere. Turned out that tiles have been falling off during launches, and that led to that disaster. That was 2005. They found this object orbiting in the air. These guys here, Mike Brown and his team, found that this object they called Eris, orbiting way out in the outer part of the solar system. I mean, the way they find these things is just take pictures, and you just look for anything that moves on the pictures, and if you take enough pictures, sooner or later you'll find something that's moving, then work out its orbit, and that's how they found Eris. And Eris is just a brighter version of lots and lots of those things out there. So there's lots of objects like Eris out there, orbiting way beyond the orbit of Pluto and Neptune. So it's got a orbital period of 557 years. So that's a lot longer than the planets. But so Eris is it also turns out it's actually got a moon in its own right, so we now know that too. So, but the outer solar system is full of objects like that. But that was the first one. Initially, when they saw it, it looked like it was bigger than Pluto, and was announced as a 10th planet. But the IAU didn't like that, so you probably see in a minute that the IAU have a way of solving these problems. So this is their solution. So in 2006 they demoted Pluto from planet to dwarf planet. Had no business being a planet. That was the International Astronomical Union. I totally agree with that. And this was a new definition of the word planet. So the IAU rule is now a planet has to, it's got to orbit a star. It's got to be massive enough to assume hydrostatic equilibrium. That means it has to be a roughly round shape. In other words, enough mass to pull itself into a round shape, and have also, importantly, cleared its orbital environment of all other things because it's smashed into them or thrown them out. In other words, it's the head honcho in that piece of space. Now, of course, the Earth is rotating on its axis, and so it's a bit fatter, and it's not really a sphere, it's an ellipsoidal shape because it's fatter at the equator than the pole. That's allowed, that's okay, that's hydrostatic equilibrium of a rotating object, but it can't be a long torpedo-shaped thing and like Eros and some of these other objects. So that was so Pluto was kind of round, but it didn't have enough mass to clear it. So there's lots of other things out by Pluto. Pluto just happens to be the nearest of a whole bunch of these things. So it hasn't cleared its part of the solar system at all. It doesn't have the mass to do that. So it deserved to be sent to the bin. So this was in 2012, the first direct evidence of black holes. So although theorists could calculate that we expect to see a black hole here, and we get observations that sort of confirm or look like that, it's another thing altogether to actually looking at one. So the Pan-STARRS telescope in Hawaii was used to take images of this thing here. This is the center of the galaxy M87, which has a supermassive black hole in it. They were able to sort of map in detail right in close to it, so you could actually see the stuff spinning around. This galaxy's, what have we got? It's 2.7 million light years away, yet the telescopes can resolve what around that tiny little dot in the very center of that galaxy is doing. So that's by getting telescopes all over the planet to get interferometric matching of the number of different optical telescopes and other wavelengths to resolve what's happening right at the center. So that was the first direct visual evidence of a black hole. 2013 was the first extrasolar asteroid. That's basically an asteroid that's orbiting another star, not the sun. So it was found to be orbiting a white dwarf called GD61. And the reason they found it was actually an icy body orbiting this white dwarf, but it was in quite a long orbit, and as it came in on its closer path to the white dwarf, it got evaporated. So it was a chunk of ice, essentially, and what they detected was the spectral signature of the water suddenly appearing. So it was an icy object that had suddenly become evaporated, and they were able to work out the orbit of it and so on. So that was kind of interesting. So And the star itself was a star similar to the Sun, but about 3 times heavier. So the nearest star to the Sun is Proxima Centauri, which orbits the Alpha Centauri double star. So Proxima is orbiting that, and so Proxima Centauri is actually, quite close to us. But anyway, they've now found this in 2016 a planet orbiting that closest star basically to us. So it's the closest known exoplanet to the solar system to date. So if they wanted to go there, they could. That's the sort of the technical details. But Proxima Centauri is part of it. So Alpha Centauri you've probably seen in a telescope as two stars similar to the Sun, roughly. So Proxima Centauri is around about, relative to Alpha Centauri, it's about 2 degrees away, the pair, and so this is a companion as Alpha Centauri C, essentially. And so currently it's quite a long way away. It's 0.2 light years away from the ones you see in a telescope, Alpha Centauri. So that's quite a long way away. It's an orbital period of about half a million years or so. So that's right on our doorstep. 2016, Oumuamua. Do you remember Oumuamua? Yeah, wasn't that extraordinary? So that was the first interstellar object ever detected passing through the solar system. And there was serious talk about setting up a thing to chase it down. They reckon if they launched a satellite that could track it down at the right speed, they could track it down in about 30 years. Well, I won't be here to see it, so I'm not too worried about that. But anyway, Oumuamua, the weird thing about it, the very first time an object from outside the solar system has come in almost within reach of it, it's probably been happening for a long time, but we just never had any capacity to find these things. But the weird thing was its shape. You probably remember all the discussion about, of all the shapes. But if you think that a lot of the objects of that general size are the results of 2 planets smashing into each other, then it's not totally ridiculous that you'd end up with a lot of shrapnel floating around out there in the galaxy. And it clearly has no way, but its shape, it sort of led to a lot of speculation about whether it was some sort of from some other civilization, da-di-da-di-da. But 2017, this was a binary merger. So basically there were 2 massive stars. They both eventually exploded as supernovae, leaving behind neutron stars. So this was 2 neutron stars now, what was left behind, whizzing around each other. And gradually, over a long period of time, those neutron stars gradually run radiating energy, gravitational energy out, and they gradually get in closer and closer and closer until they finally merge, boom, into a single object. So this was what was actually observed by this. You can see here that this was okay. So these are very sensitive radio telescopes. No, beg your pardon, they're not. They're gravity telescopes. They're measuring the expansion and contraction of space itself. So they're big, like 4 kilometre long tunnels under the Earth. And they've got 2 arms, and they've got these super sensitive lasers that go up and down. So if a gravitational wave passes through the Earth, it stretches space in different ways, so it changes the length of those mirrors apart, and that's what they can measure with these LIGOs. So there's several of these, one in Hanford, which is the eastern United States, I think in Livingston, Western, is it? So they're 4 kilometres long, so they're super sensitive to any sort of distortion to the Earth caused by gravity waves passing through the Earth. So those 2 LIGOs saw it, Virgo didn't. but it didn't matter because they were able to confirm that was the first gravitational wave observation that was actually confirmed by non-gravitational means. The 5 previous ones were merging black holes, so there was no electromagnetic part, so you've got 2 black things basically merging. You get space getting rattled and stretching and so on, but you don't see any signal. But in fact, this merger was seen in the optical and all sorts of other wavelengths by over 70 observatories because they knew it was going to happen. They knew this was winding down, so they had all these telescopes set up to measure it. So all across the Earth they saw the same event, and by combining all that together they were able to really sort of analyse this thing, this rare event amazingly well. So and in fact the merger came from another galaxy, so it wasn't nothing to do with the Milky Way, it was just something, and there's millions and millions of galaxies out there, so these sort of events are happening all the time, so they're likely to be able to get more and more of these events. You could wait a long time before one happened in the Milky Way. 2019, so China managed to soft land a spacecraft on the moon. We don't hear much about it, unfortunately. And it's got a little thing that walks around on the moon. But the challenge here was that they landed on the backside of the moon. So in order to do that, to talk to it and get anything from it, you have to have something else going around the moon, acting as a repeater station basically to talk to it. But so I understand it's still operational, but it's been up there for a wee while now, 3 years. 2019. So this was another experiment that was what was called the Event Horizon Telescope, a bunch of telescopes all around the world that looked at these, looked for these events. So this was the merger of supermassive black holes in a galaxy, which was M87 again, which was a massive galaxy. And I presume that they simply, and these are all the, so basically if it's just 2 black holes merging, there is no electromagnetic signal. You just get the sort of warping of space. But in this case, there was signals recorded by all these different satellites and everything else. So it was shadow spin. Yeah, so it's a Kerr black hole. Kerr was a New Zealander who first worked out the physics of spinning black holes and what should happen to them. So that was good that a Kiwi was there. This is the Event Horizon Telescope. So this is basically, this is again looking at M87, Virgo A, first image of a supermassive black hole. So this is in the middle of M87, which is quite a long way away, but they were still able to resolve it. So basically what they're doing here is they've got a whole lot of telescopes all over the Earth, and they're getting the more recorded, the same event, and then they can combine those images to get super high resolution, basically. And I think that image there is from the 4 8.2 metre telescopes on Paranal, the ESO's telescope. And when you do that, you get this super resolution image, and it's equivalent of seeing a tennis ball on the surface of the moon. So it's a big step up in what can be done. So NASA then sent its Perseverance and Ingenuity, its latest mission to the moon, to Mars, And so the notable thing here is this little guy can go flying around on Mars, and you've probably seen all this, but that's it. It turns out that's it flying away there. So it's just quietly, it's going to be up there for a long time yet, exploring Mars. Amazing technical feat. So the James Webb Space Telescope, which as you know is up and working, considering all the things that could have gone wrong with it, it's been phenomenally good. The images are extraordinary. You've probably seen them online. They're just unbelievably sharp, and so it's going to revolutionise astronomy. So it's basically a 10-metre size mirror up in space. It's parked at the L2 point, which means that the Earth is always between it and the Sun, so it's in the shadow of the Earth permanently. So unlike that picture.
Actually, I think, Grant, they don't have it in the shadow. They leave it out of the shadow because they can't afford for it to move in between because it causes thermal shock. So they actually have to leave it out of in the sun all the time to power it.
Oh, that's right. Yeah, so right. So they've got the shade is what they're
shade
using.
stops
Yeah.
it.
No, thank you, Bill. Yeah. So that's right. So it's but that's a phenomenal resource. The James Webb Space Telescope. It's only just started work really, and it's going to be going for quite a long time into the future. And this is the last slide. This is just an image of the Ring Nebula with the James Webb. If you've got the original off their website, it's absolutely unbelievable. You can download these humongous images, which are super high res. Looks much better than projected on there. So I'd certainly encourage you to sort of go into the website and download those images. And I expect there'll be lots more to come. So that's it. That's it. I'm happy to answer any questions if you've got any.
If anyone's wondering what's happening to the observatory today, if you've gone past it, you've noticed this is a construction site. So it's getting a new roof and a new shop and new displays. So hopefully it's going to take a while to do it. It should be open at the beginning of June if everything goes well, but who knows with builders.
What do you think might happen in the next 100 years?
I don't know. It's hard to predict. I mean, basically, I think there's other issues that are going to overtake Earth. I mean, it's the issue with climate is going to be one of the biggies. I think that in another 50 years, people will have other things to worry about than looking into space, and they'll look back as a golden age back here, and why did we stuff it up so much? That's what I think. I think it's hard to know what they can do to reverse what's happening at the moment. We're seeing the effects of it right now with the climate change, and I suspect it's in all the predictions of climate models is just going to get worse. So places like Tauranga and other places that have been hammered might just become unoccupiable. So I think other imperatives will face humanity in the 50 to 100 years from now. The global heating, there's no way to reverse what's happening now unless you really need to stop the CO2 into the atmosphere, which is, it's got a time scale of 100,000 years before it clears. So methane's better than that. But so it's a pessimistic thing. I kind of think that I've lived through kind of the best part where we learned all this stuff, and considering what was known when I started astronomy and what's known now, but I can see that ultimately it'll start to tail off as climate issues just overtake everything else. The sea level's going to come up as well because there's nothing to stop the melting of the ice caps now. So That's just my personal view.
How many people do you think will be living on Mars in 100 years' time?
Well, that's, I don't know, but, well, you know, it could be, but I mean, it's, you know, with an atmosphere about 3% of Earth's, that, you know, you.
I often tell the story about my father-in-law, who was born on the 26th of April, 1923, just after the first meeting, and he lives in Campbell Road. He's still alive.
Oh, right.
And I've already written to Prince Charles to tell him, King Charles, to send a telegram. But I often tell the story when I'm talking to people about astronomy, that when he was born, we thought there was only one galaxy. And we thought Andromeda was...
Couldn't resolve the stars in it to know.
So when he was born, the general theory was by most astronomers that there was only one. And today, what a change
Yeah.
in that 100 years.
That's right.
One to we almost thinking infinite.
Yeah. And the changes are, yeah, those were the sort of some of the big issues that really just put all the general picture together, and now they're sort of getting down into the weeds and, you know, discovering all sorts of other wonderful things about understanding the physics and the actual back to way before, people I know in the physics department here that sort of model the cosmology. Less than a microsecond of the Big Bang, they're understanding the physics of all of that, but it's, yeah, no, we've come a hell of a long way in the 100 years that society's existed. When you look back and imagine attending an Astronomical Society meeting in the 1920s, it would have been, you know, people just sitting around, maybe talking about their latest thing. They'd drawn a picture of Jupiter on some little telescope, and that was what amateurs did then. We're lucky now that we are actually able to contribute with relatively small telescopes, which is what we use, like from the microlensing stuff that we do. Those are small telescopes, but it's still, you know, useful science at the moment anyway.
From the internet, Jenny McCormick points out that you missed an important event, which was a 1 in 3,921,910,064,328 occurrence. Do you know which one it was?
No.
The Auckland meteorite.
Yeah, thank you, Jenny. Yeah, so...
And Stephen Grace says, nice jumper.
Yeah, I'm actually starting to get a bit warm.
Another question.
Yeah.
You talk about history and the cosmology back to the Big Bang, and I guess one of the things which is astronomy related, but you didn't talk about was CERN and the Large Hadron Collider and our ability to understand the physics of the Big Bang.
Yeah,
And
well,
the
yeah, I
discovery
mean,
of the...
you're right. One is I don't know that much about it, and two, but it is right. I mean, they're looking at the fundamental, so CERN is looking at the fundamental structure of physical laws that run the universe, basically, at a very high energy scale, and hopefully they'll learn something that might help us survive in the future. But at the moment, they do amazing stuff there. But it's
I mean, for me, that's the breadth of astronomy, cosmology, astronomy, astrophysics, from the very, very small to the absolutely infinite.
Yeah, that's right.
When you actually get down inside CERN,
Oh, you've been there?
Yeah, we went right down inside, but it was split down. And the actual detector would not fit in this building. And yet it's a 1 micron stream of photons that's racing through the middle of it. It's just mind-boggling to see it. And
Did you jog around the tube?
It's 26 kilometres. And you have to have your passport if you're a Kiwi, because you've got to go from France.
Yeah, it's under the border, isn't it?
Yeah. But it's well worth a visit. Well, now it's not. It's all closed up.
Yeah.
Grant, would you rate the last 100 years the most interesting 100 years?
Yes, in some ways. I mean, when you sort of lay it all out over a century, what we knew in the 1920s compared with what we know now and what we can do now, even just like an amateur body like ours in terms of understanding the science, it's so far ahead It's hard to know that you'll see something similar into the next 100 years in terms of a change. You'll see probably new technologies, but you know, when you get down to the sort of level of physics that they're doing now, it's hard to sort of see where you go from there. I mean, you could just try and build bigger and bigger accelerators or something and so on, but you talk to someone like Richard Easter at the physics department, who's a sort of basically a cosmologist physicist, and so he could probably better answer the question. He'll have questions that I haven't ever considered, so there'll be things that he would like to see done over the next 15, 20 years, probably almost certainly would. I don't know what they would be, but I think in my lifetime it's come just a phenomenal way. So it'll be for younger people, very few of them are here, but one or two, who will see, you know, stuff, you know, another 20, 30 years and probably be doing doctorates or something in those subjects, right? So that's the stuff. No pressure. No. I never imagined doing a doctorate. It just happened. Anyway, so.
Okay, well, thanks very much,
That's
Grant.
right, Will.